Ability to optimize intended function is an important skill in any branch of engineering. In this lecture, we'll talk about some problems related to engineering optimization, and we'll then formally define the optimization problem. As we mentioned, the task of an engineer is always to optimize a process or certain piece of equipment. Let us take an example. We use this example of our parachute problem that we have discussed multiple times before. We are supplying food or other essential items in a disaster-affected area using a parachute, and the total mass of food we want to drop is capital M. From the height where we will release the parachute, maximum that can go up to H, and then we have maximum allowable speed at the ground level is U0. We don't want to go beyond U0 because that may destroy the payload, in this case the food, when it hits the ground hard. So now, if we have higher payload, it will increase the speed, and then again, in the same manner, the food will be destroyed. On the other hand, if I have lower payload, then it increases the number of parachutes that we have to bring, because the total mass of food is a constant. Less amount of food per parachute means more number of parachute, so which will again increase cost. So you can see that this is indeed an optimization problem. So here our goal is to minimize the cost of parachute subject to a constraint that this U, the speed, downward speed of the parachute will be less than U0 at all time. It will be maximum just before it hits the ground. So we can take that. If at that point it is less than U0, then we are okay. So now we have to see that what we can do about this optimization problem. Our number of parachute is definitely greater than or equal to 1. We are using at least one parachute, otherwise this problem has no meaning. And therefore, payload per parachute is small m, which will be capital M, divided by number of parachute n. And we also know the mathematical model of the parachute. We have solved this before. We know that U as a function of t can be calculated from the momentum balance, that is m du dt is equal to mg minus c u square, and c u square is the drag force. Here m is the mass and u is the downward speed, and c is a constant which is proportional to this area. So when we say it's constant, it means that it doesn't change with t, that is what we have assumed here, but it may vary with the area, that means the design of the parachute. To solve this differential equation, we need an initial condition, and that initial condition is u time t equals 0 is equal to 0. So we know the release height, that is h, that equals 0 to t0. T0 is when it will hit the ground. U dt, that is the release height. We can find the time required to hit the ground from this, and this t0 can be calculated from this integral. Then once we know the t, the speed at ground level will be u. U will be solved from this equation, and t equals t0. It should be less than or equal to u0. That is the requirement for us. We have solved this problem before. We know how to solve it. So that is not a problem for us. But now we include a cost model in this. So this is our total cost, and our total cost consists of several components. It is multiplied by n because this is cost per parachute within the first bracket. So first there is a fixed cost. Fixed cost can involve many different aspects. We will not get into the detail. Then the chord that we have here, these are the chords I have. These chords, we have to take care of that chords. So some constant multiplied by the chord length. Then the chute costs, that means this canopy that we have in parachute, that should be some constant multiplied by the area. And then if I want to make a large parachute, then I have to add additional cost. So this cost of the parachute is not just for A, it is also proportional to A square. So we have taken a nonlinear model of cost with respect to the area of the chute. This is because the cost increases rapidly. For manufacturing large chutes are not easy. Now we can think of that this radius here is r, and therefore this chord length L should be geometrically somewhat proportional to r, and the parachute area will also be proportional to r square, etc. So I can write this model in terms of r, and it can come as this capital C total cost is n multiplied by this C0 plus C1 plus C2 C3 with this constant C1 r plus C2 r square plus C3 r to the power 4. So this C1 to C4 all are constant, and this C4 is coming for this drag force. We have a constant C here, so that requires C4 multiplied by r square. So you can see that cost is now a function of r. Everything else is a constant, and for now we can just assume for simplicity that we know all this constant from C0 to C4. So therefore, the cost minimization problem of the parachute comes like this. We have to minimize this cost C, which is n multiplied by n is the number of parachute, multiplied by this C0 plus C1r plus C2r square plus C3r to the power 4. And now you may wonder that what are we talking about? This r, if I make r small, then the cost will be small. So if I make r close to 0, that is the smallest cost that I can get. So this is not a big deal, but wait, there is more into it. What comes from the constraints? So constraint is that this u at time t equals t0 means just before hitting the ground, it must be less than certain specified speed u0. So if I reduce r, my parachute will be smaller and smaller and it will hit the ground hard. Parachute goes smaller and smaller means it is as good as a free fall of this payload. So it will hit the ground hard. So I cannot just keep on reducing this radius r. At some point I have to stop. So here I know that this u0 I have to calculate because u0 is not given here. And in this u0 calculation, I have this m by n, that is the payload small m. So small m is capital M by n, du dt minus m by n g minus c4 r square u square. So if I reduce r too much, then this drag term will vanish and the payload will hit hard at the ground. So r, that is the variable I want to play around to minimize the cost C, that r also appears here. So the overall problem now you can see that we have to minimize this, but subject to the constraint that this u will be less than u0, and then u depends again on r. So we have all these known parameters, this c is, including this c0, these are all known parameters. And now we have to optimize this capital C, the total cost. So now we are ready how to make a statement of optimization problem. We are not going to optimize this. This is a very easy optimization. You can do it because we have already solved this problem. For you, it should be very easy. You can try it yourself. But then we will now define a generic optimization problem. And in an optimization problem, what we try is that we try to minimize some function of x, and this function we are trying to minimize is called the objective function, which in the case of our example, that is the cost of the parachute, that is the objective function. And the cost of the parachute depends there on r, but in general, it may depend on more than one variable. That is why we are bringing a vector here, this x, that is the design vector or the design variable, which we will vary to minimize this f. Now we have certain constraint that we have already seen that in our case, in the example case, u has to be less than u0. So here we can have certain constant. For instance, certain function di x should be less than ai type constants, and these are something we call inequality constraints. We may have m number of inequality constraints. Similarly, certain other function ej of x is equal to bj. These are equality constraints, and you can see that we have p number of equality constraints. So this is the basic structure of an optimization problem. Now, this generic structure is something we call constrained optimization problem because we have constraints. If we do not have constraints, then the problem comes as unconstrained optimization problem, and we'll talk more about this unconstrained problem. In fact, we will talk only about this unconstrained problem later on. So in unconstrained problem, you have no constraint, means this MP there 0, so you have no constraints. And this objective function here, usually that objective function we consider as a scalar valued function. So we have an input x that is getting into this function, but its output is a scalar. Input is a vector, in general is a vector. In our example, input was also a scalar, but in general input could be a vector, which means basically that there may not be one input, there may be many inputs. Now, depending upon the nature of the objective function as well as the nature of the constraints, there are different types of optimization problems available. One is linear programming, where both objective functions as well as the constraints are linear. The second type is this quadratic programming, where objective function is quadratic, but constraints are linear. You may have this kind of situation many times in, for example, in a regression problem. And third is all other cases where at least some of them will be nonlinear, and that is in general we call nonlinear programming. Quadratic programming also, we can say that this is nonlinear, but there are certain special tools sometimes we use when this happens, when objective function is quadratic but constraints are linear. That is why we keep him in a separate category. But certainly these come within the bigger domain of nonlinear problems. Now you have seen that while formalizing the optimization problem, we have talked only about the minimization. So what about maximization? Sometimes we are interested about maximization of certain variable, and that is obviously possible. If we want to maximize fx, that means we want to minimize the negative of fx, we can name it phi x. So if this is my fx function, we want to maximize. If I reflect it with respect to x-axis, I get this negative fx. You can see that getting the maximum of fx now comes down to getting the minimum of negative fx. So that is why all problems in optimization, we pose them as a minimization problem, or we define them as a minimization problem. When you solve it, you can solve for maximum. There is no issue with that. But formal definition we give in terms of minimization. The second issue in optimization is that a function may have multiple minimum, multiple maximums. So that is where this local versus global, this idea comes. So here in this function, you can see this is local maximum and this is global. Here I have this local minimum, here it is global. So functions usually may have multiple maxima, minima, and the minimum of local minimums, that is the global minimum. Now if a function has many minimums, then that is always a problem, especially for engineers. So when we are searching for minimum, in most cases engineers actually look for global minimum, but when we are solving, we have to be careful. We cannot get stuck in a local minimum. That is why there are certain school of functions which we call convex function, which is a function that will have only one minima. That means the local minima will be global minima, and that is something very useful in engineering. We try to pose different optimization problems in terms of optimization of convex function. Now to summarize, in this lecture, we have formally defined optimization problem. We have also discussed an example. For your exercise, you find out 2 examples of constrained optimization problem, and similarly, you found out 2 examples of unconstrained optimization problems. Thank you. That's all for this lecture. I'll see you in next class.